afternoon session of our of the workshop, and I'm very happy to introduce our first speaker, Tom Y.Hou from Caltech. Tom Y.Hou got his PhD from UCLA in '87 with Bjorn Lundquist, and then he had a couple of postdocs, I guess just one postdoc in Courant, and then stayed there for a little bit, and then became a professor at Caltech. Among many honors and awards, he recently became a fellow of American Academy of Arts and Science, for example. Tom made fundamental contributions to numerical homogenization and singularity formation in fluid mechanics, and numerical analysis of singularity formation in fluid mechanics. And today he is going to talk about Bayesian interference and multi-scale invertible generative networks. Please, Tom.
Thank you, Alice. And thank you thank the organizer for inviting me to give a talk in this very stimulating workshop. I have enjoyed it very much so far. It's been a very interesting and dynamic workshop and cover a lot of recent developments. So today I want to talk about my joint work with my former PhD student Pengchuan Zhang. He's at Microsoft Research, and my current PhD student Sumo Zhang. So we encounter many inverse problems in our life, in our scientific research. So very often we have some kind of measurement by solving a physical problem, like a follow problem. But we would like to infer the coefficient, for example, or boundary condition, and in the physical system, we denote as X, right? So X is some measurement that we have by solving a follow problem, but with noise, often with noise. So that's the measurement we have. We would like to solve the inverse problem to characterize what the kind of X will match the measurement Y, right? So that is the problem that we often encounter. So there are several approaches that people solve this problem. So typically, when people would use optimization to trying to minimize the data mismatch between the observation and the physical system, right? Sometimes you use regularization, or sometimes you don't need to use regularization, right? On the other hand, we know that due to the noise, there's a lot of uncertainty in the recover solution X, right? And also in many cases, due to limited measurement, so the X is not unique. So you have multiple mode that we still keep the same measurement. So using an optimization approach may not be optimal for doing uncertainty quantification. So people often turn to in more recent years, the Bayesian inference approach, right? So the Bayesian inference approach can be characterized very simply like by this Bayes rule. So we know something about the pi distribution of X, right? And then there's a likelihood function that basically measure the mismatch between the measurement Y and the forward solution given X, right? If you know the distribution of the noise, the noise error, so then you put the P is the density of the noise, right? So then you have the mismatch, and Z is a normalization constant, right? So that is the Bayesian's formula. So that has a good advantage that, in the sense, if you know the posterior distribution, given the measurement Y, you can quantify the distribution over X. Then you can do all kind of UQ, right? And so quantify the uncertainty. You get a full characterization of the all possible solution, right? And then you can compute the statistical quantity of interest that any function f is a function of X. And then you can compute their expectation, for example, right, or higher order moment. But the problem is this it's not completely solved. Just even though we have this Bayesian formula, especially in high dimensional case, because it's very hard to generate high quality sample from the posterior, right? So having a high quality sample is very important, because when you're trying to evaluate this as statistical quantity, you for example use Monte Carlo method. So you would like to generate an IID sample that would match the posterior distribution, right? But especially in high dimensional case, that the importance region may concentrate in a small subset of a very high dimensional space. So in order to capture correctly the important region, the computational costs typically grow exponentially with respect to the dimension. Well, a typical method to solve the basic inverse problem is using the Monte Carlo, Markov chain Monte Carlo, right? So that has been used widely. So that is like the method of choice in many cases. But you also suffer from some drawback. For example, the mixing rate is very slow. It takes many iterations to get fully mixed, and it still suffer from the curse of dimensionality. And the sample that generated the sample are typically correlated because you sampled them in a sequential manner, right? There have been various proposals to remedy this limitation. For example, people propose a Hamiltonian Markov Monte Carlo. There's a MALA method, right? And there's many subsequent developments. So I list some of the reference here. And in more recent year, there was another interesting development using the so-called Stein variation of gradient descent, right, inspired by the machine learning community. So they trying to minimize the kernelized Stein discrepancy at each time step, right? So that is offered a very interesting alternative to MCMC. But however, it still suffer from the mode collapsing, meaning that you may not be able to capture all the possible mode that match the measurement, especially in high dimensional setting. So there was another approach that doing sampling without chain. So using a transport map, using a variational inference. So I think this approach can go back all the way to maybe the early work of Alexander Chorin in 2009. He introduced so-called implicit sampling. So there he introduced a map that you map a very simple, easy to sample distribution into your targeted distribution. That once you can construct such a map, then you very easy to generate sample, right? But on the other hand, his original method required the target distribution has certain nice geometry. For example, have a U-shape assumption, more like a convex, locally convex in some sense. And this approach was further developed by Mazuz and his group. And there he really formally introduced a transport map. And the map was constructed by polynomial basis, right? So that again has the same philosophy. You consider the map to map easy to sample distribution to your target distribution. But due to the fact that he parameterized his map by a polynomial basis, so it still suffers from high dimensionality, right? It still suffers from the curse of dimensionality, right? And that means there's been many following work, and more recently, I think that they also trying to explore a neural network kind of structure. Okay, so I would say that for dimension as higher as 1,000 or above, so the best method, the method of choice are the Hamiltonian Monte Carlo, or the Monte Carlo or MCMC with different kind of preconditioning proposal. For example, the Pi precondition Cran-Nicholson random walk, or using the Hessian precondition explicit Langevin proposal, and so on. And also the ensemble common filter is another very popular also. So the approach we are going to adapt will be use a transport map by using a deep generated network to characterize the transport map. So let me say a little bit more about this approach based on the transport map. So suppose you have a reference probability measure, so that is easy to sample, right? For example, could be a Gaussian. So you like to construct a transport map F, capital F, right? So this is not the same thing as the curve F that would describe the forward process. So then you construct the push forward map, push forward distribution defined by this, right? So F inverse A, it is for any measurable set A, is the pre-image of the set A, right? So you basically try to map a easy to sample reference distribution, new ref, into your target distribution, right? So then it has a lot of advantage, right? Because once you can find such a map, the push forward map, then you can generate a sample in the reference probability space, and then you map to the target distribution, right? So then you can generate IID sample very easily. So if you further assume that the map, the transport map is also invertible, right? So then you can also characterize the density of the push forward map, right? By this change variable, right? So the invertibility is required because you need to compute the Jacobian of the inverse of the map. So this is a further illustration that suppose you have in the reference measure, it is a Gaussian measure, which is very easy to generate sample. And then you construct a transport map, should be capital F here, and then you map into a much more complicated targeted distribution that have multiple mode, multiple cluster, right? So then once you have that, then it's very easy to generate sample because generate a Gaussian sample is very cheap. It's cost nothing. And then once you train the map, so you can get the target distribution for free, almost for free, and then you guarantee to be IID sample. You don't need to worry about the correlation among the different samples. Okay, so then you would like to parameterize this map by a parameter family, right? Theta in some huge parameter family, right? So P theta it is a distribution for the targeted distribution, approximation for the targeted distribution. So it will be parameterized by theta. Then you need to introduce a discrepancy, some kind of metric to measure the difference, the discrepancy between your push forward map, the transport map, and your targeted distribution, which is given by the Bayesian inference, right? So then you want to choose a theta, the parameter, to minimize the discrepancy. Okay, there's many possible choice for the discrepancy. D, I will come back to that later. Okay, so that is how you formulate the problem, right? Formally, that's how you formulate it. So possible choice for D, for example, so in recent years, there's a lot of this work that use the K-out divergence, right? So that could be one possible choice. In fact, that's the choice we adopted in our previous paper. And you can also use a kernelized Stein discrepancy or the maximal mean discrepancy or Weissenstein metrics and so on. But on the other hand, you have to be aware that keep in mind that the fact that we don't have sample for the targeted distribution Qx given by Y. We only know the density, right? And so in fact, to evaluate the density, you have to solve a forward problem. It could be very expensive, right? But we have sample from the transport map, the P theta, because we construct the map ourselves. So we are able to sample. If the map is further invertible, you also know the density, right? So that is the dilemma that we are facing, that in order to choose a proper discrepancy, that you need to take into account the fact that we don't have sample for Q, right? So that limited the choice, what kind of discrepancy metric that we can use. All right, so I mentioned earlier that the transport map that I used earlier, introduced by Mazouk, as is used polynomial basis to characterize the map. So in our previous paper that published last year, in a special issue devoted to machine learning, we use a deep generative networks, right? But at the time, we used the KL diversion, but without using the invertible, the map is, we do not require the map to be invertible at the time. Okay, so the advantage of using a transport, constructing a transport map is there's several fold, there's several factors. First of all, once you construct the map, it's super efficient to sample, and then the sample are guaranteed to be IID. And it has a very large capacity, right? So because you use a deep generative network, neural network, so there's only very weak dependent on the dimensionality, right? Unlike the polynomial basis approach. And it's also very scalable. Suppose you have access to much larger computing capacity, and then you can build a larger network, and then you can get a better result, more accurate result. So there's you don't need to change the network, right? It's more computer, the faster, the same setup. So this is an example that people use the deep generative network to study human face, right? So you can see that you start from like a 100 Gaussian random variable on the very left end is the input, and go through a sequence of a neural network layer, and then you output a 64 by 64 dimension of human faces. Right here, it is a collection of all different human faces. This is all, of course, is a kind of fake faces because you generate from random noise, right? But you learn from a dictionary, from a big, huge library, right? But each one of them looks very, very realistic, right? So that shows that the deep generative network has a very large capacity indeed. So we would like to see if we can take advantage of the large capacity offered by the deep generative network to construct the transport map for our purpose, right? So a few things you have to keep in mind that the problem we trying to target is very high dimension. For example, when we in one of the example that we study is the groundwater transport, right? So the axis is the probability coefficient, for example, right? So if you discretize a problem on even on a relatively coarse grid like 64 by 64, so you have a huge number of degree of freedom to characterize this probability, so the dimension easily can go up to 10 to 1,000 or more, right? So we're talking about very high dimension random field here, right? And then we also realize that the anomalized, the posterior, the Bayesian distribution is computationally intensive because every time you want to generate a sample for the targeted distribution, you need to solve a follow problem, which is the groundwater problem, which is very high dimension. You have to solve it, very, very expensive to generate one sample, right? And also we know that due to the uniqueness of the elliptic problem, that you have a multiple mode, meaning that you, for the same kind of measurement, that you can have multiple choice of the coefficient that will match the same measurement, right? So we would like to capture all the possible mode, right? Physical important mode, not just one of them, right? And we also interested in the problem when the physical problem has multiple scale structure, right? So that all this make it the problem much more challenging. So this is what the major ingredient of our approach. First of all, we adopt a deep generative network to construct a transport map. So we choose this deep generative network because for its large capacity, weak dependent on the dimensionality, and also very naturally fit into the multi-scale feature that we use a core scale solution, which is low dimension, and then to provide a good initial guess for the finer scale solution. And we do it in a recursive manner. And we use the invertible maps so that we allow us to use the Jeffrey divergence that we will introduce later. The KR divergence tend to miss some of the mode. So you have a mode collapsing. So the Jeffrey divergence make it much easier to capture multiple mode, but then it's harder to generate a sample. So using invertibility, we are able to use important sampling to enable us to train a deep generative network that using the Jeffrey divergence as the discrepancy. So the main feature is that we use a multi-scale structure, multi-stage, multi-scale structure, plus invertible transport map, so that we can recursively train from coarse to fine to generate a network in a multi-stage manner. So that is really the accent, the key to our approach. Okay, so let me briefly review an important observation that we make in our previous paper. So when we studied the elliptic equation, a multi-scale elliptic equation with the quantity of interest is the probability field, is the log of the probability field equal to x. That's what we're trying to infer. Okay. So then we found that if you solve the problem, for example, on a fixed scale, 64 by 64 grid, but on the other hand, the coefficient, the probability coefficient, you can sample them at different scale. For example, where it calls A by A, 16 by 16, 32 by 32, or 64 by 64, right? So we observe that the MAP estimate, the maximum a posteriori estimate, they have very good resemblance in the neighboring scale. For example, A by A and 16 by 16, you can see although this is coarser, but you see that the major feature has been captured by the coarser grid. And similarly, 16 by 16 to 32 by 32, you see that there's a similarity. Of course, the 32 by 64, you can even get a closer approximation. So this suggests that we can actually use the coarse grid solution as a good approximation or preconditioning, a good initial guess for the finer scale, right? So that is the take-home message we have. So in order to show how you can benefit from this way of thinking, so let me give you a little bit of the mathematical detail. How do we take advantage of this observation? So we say that the likelihood function L, Y, X has a multiple scale structure if for a deterministic downsample operator A, for example, could be a local pooling, average pooling, and then you can have an associated coarse grid likelihood function LC, Y given XC, with a dimension DC is less than the fine scale D, so that the likelihood function can be approximated by the Coulson likelihood function, right? That replace the fine grid the measurement, the fine grid coefficient X by the coarse grid projection, right? So that is the observation that we make in the previous paper. And if you then we can use this observation to design our training strategy, right? So in order to sample from the pi distribution rho of X, we want to generate a sample from the coarse grid pi distribution rho C, which is the downsampling the rho into the coarse grid, right? And then from there we can generate a conditional probability distribution using the condition probability rule, right? So that is how we do it. So instead of sample directly from rho, from the pi distribution, we first generate a coarse grid coefficient XC from the coarse grid pi distribution, and then we upsample it to this to X using this condition probability that defined like here, right? So I would like to make a remark that this upsampling step is similar in spirit to this prolongation operator in multi-grid, but except that now we work in the stochastic way, stochastic manner, because we have the random noise through the distribution, right? So it's like you condition on the coarse grid distribution XC, that you add some random noise through the pi distribution, and then you fill in get a more detailed prolongation, stochastic version of the prolongation operator. And then let me explain how we use this observation in our training process. So as I mentioned earlier, that this is our targeted distribution from the Bayesian inference. Then we say that due to the multi-scale structure that we can approximate it by corresponding coarse likelihood function LC, the condition replace X by the downsampling operator. And then we further split the rho X into this product. I just show you that using the condition probability, can you first sample from the coarse grid sample, price sample, and then do the conditional probability, right? So this is the prolongation step, right? So this one you just copy down. And then you further notice that these two together, these two product together, we denote it as the QC. So meaning that this is the corresponding targeted distribution at the coarse grid level, right? There's a corresponding normalization ZC, right? So you can think about, you can approximate or decompose the original target distribution on the fine grid into a coarse grid version of the targeted distribution, right? And then based on this conditional probability on the pi distribution rho, right? And there's a scaling constant here, right? So this is our surrogate to some extent that give you a good approximation from the coarse grid to the fine grid, right? So that is our very important step that we call the pi conditional step, right? So we denote this right-hand side to be our surrogate posterior that we call Q tilde is this product, right? So this one we can compute without training at this step. If you know QC at the coarse grid, suppose after the training we get the QC at the coarse grid, so then multiply, then basically apply the Bayesian rule at the coarse grid level, you get the Q tilde. Q tilde is a good approximation to the final target distribution Q. All right. Oops, sorry. So then this is the how we turn this into a sampling strategy, right? So suppose that we start from a very coarse width XC, suppose like a 4x4, right? So which is very easy to it's a low dimensional problem. We can very easily to train to get the QC, right? We can use existing method like MCMC or the HMC. So then we can use this we call prior conditioning, which is the one that gives you the Q tilde, but based on the knowledge of the target distribution QC and the conditional probability. So you get a Q tilde, so that will generate approximate sample X tilde, right? And then X tilde is not good enough. We want to get an even more accurate approximation, the sample for the fine grid distribution X, right? So the final step is the crucial one that we train the transport map using the deep generative network, right? And then we get a better approximation for the target distribution. And then we do this recursively. So you start from the coarsest level, right? You get an approximate target distribution, the surrogate distribution. And then you train a map at this current level, right? And then you move to the next level, right? Sorry, this is the coarse level. This is the final level, like the L level and the L+1 level. And then you further improve it by training a transport map. And then you improve the accuracy of this target distribution at the L+1 level. And then you do this recursively. Yeah. Okay, so that's how we do it. So, and as I say that because, so typically we pick the prior distribution, it is some kind of a Gaussian-like prior. So we take a linear downsample operator. So then actually the prior conditional distribution rho conditional XC is also a Gaussian. So in that case, actually, you can actually pre-compute this precondition, this conditional probability rho given conditional on the XC, right? And then because the network is invertible, so you can actually, you also know the push forward density function, right, given by this formula. And the transport map that we will use a compositional approach, like in the deep generative neural network. So each F1, F2, Fn, it is a relatively simpler transport map, invertible map. We use a invertible block that's designed in the GLOW algorithm, right? So it's a smaller invertible block that's easy to construct, and then you can position them. You can make a more complicated map that has a larger capacity, right? So then in this training, so we can always start with the identity map because the Q tilde is already a reasonable, good approximation to Q. So you started with the initial guess for F to be identity, and then you train through this compositional map, then you obtain a invertible map. So this is the main training strategy, the procedure. So you start from very coarse grid, right? Then you get the using the prior conditioning, the Q tilde, you generate a finer sample, X tilde at the L level, right? And then you improve it by training a transport map, right, at the same level, at the L level, right? Then you get the a more accurate approximation to QL, and then you go to the next level, right? And then you use a prior conditioning again. You go to the L+1 level, right? Using this one, there's no training. The Q tilde is based on prior knowledge, and then you train the next level of the transport map. You get the updated target distribution at the L+1 level, and then keep going until you reach the final level, that which is your targeted distribution, right? So this is how the method work in the network. So you start with the Gaussian noise, right? Z1. So this is Z1. It is the coarsest level. So you train the map F, right? Because it's low dimensional enough, the very coarse width. So you can train the F1 accurate enough, and then you get the X1 sample, right? And then use prior conditioning PC2 to go to the next level. The next course is like from 4x4 to 8x8, and then you get the X2 tilde based on Q2, and then you train the transport map F2 using the Q2 tilde as the initial guess. But sorry, using using Q2 as the one that you can generate as a surrogate, right? So I will explain to you why we need to use Q2 tilde to train F2, because we use the so-called Jeffrey divergent, and we need to use important sampling. So we need to use Q tilde 2 to train the F2, right? And then we get the updated X2, right? And then keep going on like this. We go to 3, and then all the way to the final level. Okay, so now we come to the choice of the discrepancy D. So as I mentioned, that in our first paper, we actually use the KR divergent as a way to measure the discrepancy, right, which is defined by this. So the KR divergent is easy to use in our context because we have the transport map, so we have sample, right, from the push forward distribution P theta, right? So in our previous paper, we did not require the map to be invertible, so we don't have density, but we know how to sample it, so you can evaluate this by Monte Carlo method, right? So it's very easy to sample, right? But however, it suffered from the mode collapsing issue that we found out that which is not good, because the reason is that the KR divergent would be happy if you find one single mode, as long as the important high density region of P theta is covered by the important region of Q, then this is small. So then it's happy that then it stops the training, right? It's not going to look for another high density region, right? So that is, let me give you a toy example to illustrate this problem. For example, in this toy example, I have a sum of 2 Gaussian, one center at 1.5, the mean, one center minus 1.5. So then you can use a parametric family candidate that you find M1, M2, right? This is the mean, M1, M2, right? Even if you assume you know the variance exactly, right? So then if you compute the KR divergence for this candidate posterior, and compute the discrepancy between P, M1, M2, and Q, you find that this is the landscape, the energy landscape, right, for this KR. You can see that the golden cross is the global minimum. The true minimum, the ground truth. There's 2 possible mode here. There's 2 mode here due to the symmetry. But you also pick up 2 at the spurious local minimum, right? So it also minimized. In fact, that all local minimum are the same energy as the global minimum, right? So you also pick up the other 2, which is not the physical mode, right? So that's not good. So on the other hand, if you add the reverse KL, so meaning that KLPQ, and then also add the KLQP, right? Then you penalize the spurious local minimum, right? You only have the low global minimum to survive in the energy landscape. It's much better, so yeah, and that is the one that we are going to use in this paper, in the cover work, okay? But there's a problem. So now we change our discrepancy to this so-called Jeffrey divergent. But the problem is that we know how to compute, how to sample the KL part, KL divergent, right? Because we have a sample from P theta. This is something we construct on the fly. But here, the posterior distribution Q, as I mentioned earlier, we cannot generate sample to evaluate this. So that is the problem. And in fact, that's why we did not use this double KL in our earlier work. But then we realized that if you train the map to be invertible, you construct the map to be invertible, right? So then you also have access to the density of P theta. And also, since we use a prior conditioning step, you have a Q tilde, which is a good approximation of Q. So we can do important sampling to evaluate, to approximate this the reverse KL, right? So you change this into this discrepancy. So you do importance sampling. So the Q tutor is something we have using the prior conditioning at the current step. So we can generate sample from Q tutor. Then you can evaluate this the second the reverse KL divergence. Okay, so that's how this is how we are able to handle this so-called double KL, or also have the name of Jeffrey divergence. Okay, so as I mentioned, that the first one is easy to do because we already have sample, right? The second one we just do an importance sampling, right? Yeah. So and also then we actually, when we train a neural network, so we use a stochastic gradient descent, which involve the derivative of this discrepancy, right? And then the derivative is also known, so you can take the differential with respect to the parameter. So you have this form, and then it is important to realize because we have an invertible map. So this one, it is actually we don't need invertible map here for this one. So this can be the derivative of log p theta with respect to theta. It can be computed by backpropagation of the neural network. So this is also available. So you can apply stochastic gradient descent to minimize this discrepancy. So now go back to the just recap the strategy that I mentioned earlier. So now we already determined using a Jeffrey divergence to serve as our discrepancy. Okay, so we just go through the same step as I said before, right? So you start from the first one, and then you using the PC preconditioning 2, and then you generate a approximate sample x2 tilde, and then you go to the chain of the F2 map in this scale, second scale, right? And then you go all the way. Yeah, so that you can do it recursively. All right, so we want to show you some examples. So we use 3 examples to illustrate the capacity and the robustness of this approach. The first one uses a natural image synthesis, right? So we have a lot of database for the natural imaging, human face, basically, right? So in that case, we train the multi-scale invertible generative network by the maximum likelihood estimation, MLE, right? And this shows there's a very good capacity and also very good interpretability of this of our approach. And then for the Bayesian inverse approach, we consider 2 examples. The first example is a toy example where we know that we have an analytic as we have the ground truth for the target distribution. We construct a toy Gaussian example. So where the ground truth is known, so that we know that we exactly quantify, we can quantify that we indeed capture the multiple mode. And then the final problem is that the groundwater transport problem, the elliptic PD with a random probability coefficient, where we don't know the ground truth because you have to solve many forward problems to generate, to approximate the target distribution, which is too expensive. So we will use three examples to illustrate it. Okay, so for the first example for the human face, we use how to measure the performance. We use the so-called bits per dimension number given by this. So the smaller this number, the better, the more accurate the network is. So we trained it for a number of data sets, including the MNIST, the CIFAR-10, and SLAP-A, and ImageNet, right? So you can see we compare with different kind of a state-of-the-art method, right? All listed here is the different number of the bits per dimension number. So the last column is our method. You can see that indeed it is comparable to the best, the state-of-the-art method, right? So you can see the slightly better or comparable, right? So that is a good encouraging sign. And also, it was mentioning that our method, our approach actually use far less parameter than the globe, for example, and for example, about 24.4% fewer parameter than the globe, and 37.4 fewer parameter than the residual flow, right? So these are the state-of-the-art approach. Okay, so this is some of the randomly generated image through our transform map. So you can see that, of course, these are a fake image, but you learn from this real image, a library of real image, and then you generate a random noise, and then you output the data, right? So you can see each one of them looks pretty realistic, like a human face, right? Of course, it's a fake face. And you can also do interpolation pretty easily in the latent space, like in the Z space, in the random, the reference space. So for example, you can interpolate between a female face and a male face, right? By changing the interpolation parameter, you can change gradually from a female face into a male's face, right? From somebody have a gray hair to somebody have no hair, right? And right, you can see all kind of variation, right? So you can see, yeah, right. So you can see each one of them looks very realistic. And we also check that how does the intermediate step in the neural network, in the deep generative network, how does it work? Do they produce something meaningful, right? So that's what we call interpretability. So we in the throughout the deep neural network, so we put in some checkpoint. So we want to see that this in the course is like a course grid, and this is the next level. The next level, like a 8 by 8, 16 by 16, 32 by 32, 64 by 64, and so on. This in a different checkpoint of within this resolution. Of course, very earlier, the earliest one is just random noise. You don't see anything. But as you go through the training, you can gradually see some feature of the human face emerge. As you go to the final resolution, you can pick up more and more detail, right? And more detail. And the final one is the output layer that you generate a very realistic human face. And to the best of our knowledge, this is the first time the flow-based invertible model can actually visualize internal neural network action, that you can see something that seems to be meaningful. So the second example is a toy example that where we constructed the target distribution by two Gaussian, right? They have symmetry, it has a mirror symmetry. So we know that there was there's the two mode, right? We know there's exactly two mode mirror symmetry, right? The price distribution given by this, and then you use some measurement. So this is how we generate the measurement. So we project it to the Fourier basis of the 1 and 2 Fourier basis of this pi covariant, okay? And then this is the ground truth of we know the ground truth in this case, okay? And they're exactly mirror symmetry, that's two mode. And then the posterior is given by the product of some independent one-dimensional subdistribution, right? So this is we fixed the budget to be the number 4 evaluation to be 10 to the power 8, 10 to the power 5. So you can see that our method indeed capture the multiple mode. So the ground truth is given by the green color, right? And then the red line is our multi-scale invertible generative network. So the green and the red looks almost the same. And then the Hamiltonian Monte Carlo is the blue line. We use that as a benchmark for the groundwater case where we don't have the ground truth. It also captures the multiple mode, but it's kind of off balance, not balanced, because the two mode supposed to be exactly mirror symmetry. So we check the mean error and also the standard deviation and also the correlation error. So among all three methods that we compare here, our method seems to be work the best, the smallest error. And then so this is the one that for our final example, that when we had solved a 4 elliptic problem with 64 by 64 grid, and we have 25 local noisy measurement of U, right? Of this U is the pressure, right? And then we limited the 4 distribution, 4 problem solved to be 8 times 10 to the power 5. So you can see that in this example, you can see that the both Hamiltonian Monte Carlo and our method, the red line. So in this case, we don't have the ground truth, that we both capture the multiple mode, right? And our method is more balanced, but the Amorta Stein variation of gradient descent completely missed the double mode, right? So this is the clustering and of the 3 method, right? So you can see that our method clearly separate 2 clusters, right? HMC also do a reasonably good job, but not very symmetric. but the amortized Stein variational gradient descent completely missed the two kind of collapse into single mode, right? You can see that this mode 1 and the mode 2, and then the last method completely missed the separation of the two mode. So here we like to point out that the training is important, although we get the prior conditioning, it's already pretty accurate, but if the transform map, it further decreases the discrepancy through training. You can see that as we increasing the level, right, from the Q4 tilde to Q4, it is a meaningful change in the solution right. This is the 6th mode, right. So this want to show that the training is really important, and we also trying to I'm sorry that I almost ran out of time, but let me try to finish in a few more minutes. That we also trying to see if the prior conditioning really necessary. Can you replace by something else? For example, we test against the so-called nearest neighbor upsampling method, and also the split and squeeze method as to replace the prior conditioning step. Then you can see that in the synthetic case, where we know the exact solution, the other two approaches, the nearest neighbor upscaling and the split and squeezing, that completely miss the multiple mode, right? And the elliptic PD also the same. So the only our original method using the prior conditioning that capture the multiple mode. And we also trying to see if the Jeffrey divergent and the KL divergent, whether you can replace the Jeffrey divergent by KL divergent. So we find that actually, if you use a multi-stage, you can actually still capture the multiple mode pretty accurately, right? So the multi-stage actually play a very important role. They start from very coarse grid, then you capture the two mode, and then you pass the information on to the later, the higher resolution, the final scale. But if you use a single stage, right? If you use a single stage, like KL, then you completely miss the multiple mode, right? So this is for both the synthetic case and the elliptic case. So your single stage will fail. So you're also trying to test against other kind of, if you replace the Jeffrey divergent by the kernelized Stein discrepancy, right? So again, the multi-stage stage still work, but if you use a single stage, that will fail miserably, okay? So this is a conclusion slide. So I presented a method that using multi-scale feature and invertible generative neural network, that we can generate a good approximation for the target distribution that can have the capability to handle high dimensional inference and can capture the multiple mode. So here, using the Jeffrey divergent and the multi-stage training, it seems to be very important. Yeah, using the prior conditioning step in the multi-stage manner is very important, right? So once you train the map, so it's easy, as I mentioned, that it's very super easy to sampling. The sample guaranteed to be IID, and it's also scalable. If you have more capacity, you can always add, and then you get a better result, right? So in the future, we still have to, there's some work that we want to further improve. For example, the Jeffrey divergent, right now we use the Q tilde, the important sampling to do the training. But we find that if the Q tilde is not a very good approximation to Q at some early stage, then you may suffer from some kind of instability. So we're trying to do a better job there. And then we also would like to extend to the time-dependent problem and data assimilation and so on. So with that, I stop and thank you for your attention.
Thank you.
Thank you, Tom, for your wonderful talk.
Thank you.
John, do you want to start with the questions you haven't?
Sure. I will read. There are a couple of questions here. So the first one is that, do I understand correctly that for any new data or measurement, you need to retrain the network in order to solve the inverse problem? If so, do you have a sense for how your method compared to MCMC in terms of computational cost?
Okay, so indeed we need to retrain the neural network, but I think that we can benefit from the already trained network, right? So I think that assuming those data are not completely unrelated, right? So if you try to solve the same set of problem, I think you still benefit from it. And the MCMC, as I mentioned, that if the dimension is modest, I think that is good. So we compare with the HMC, right? So that is that's computational cost. I think is comparable. Yeah, in the training set. But our method is that once you train it, then the subsequent use is cheap. Like it's almost zero cost, right? MCMC, on the other hand, every time you have training, you have to retrain everything again, right? You cannot, when you generate new sample, then you still have to do MCMC, right? So I think that well, Sumao is my student is also here. He can also elaborate further if Sumao, you have anything to add?
Yeah, so he mentioned actually, maybe should I probably bring him to the panelists maybe?
Okay.
So
yeah.
that if you want,
Yeah, he has more domain knowledge.
Sure, let me do this quickly. Let me promote him to the panelists and maybe even a co-host so he can talk.
Great.
Hello.
Yep, so I'm making you a co-host now.
Good.
There you go.
I guess the original network can serve as a very good initialization for the new network. So I guess the training for the new network, when we have extra data, will be the computation cost will be much more less than the training from scratch.
Right. Okay. So may I move on?
Compare the MCMC, the cost. The second question is.
Yeah. The second question is, what is the effective sample size of HMC versus your method in the diffusion example? So assuming that the number of likelihood evaluations are the same.
Suma, can you comment on that?
So for our experiment of the elliptic PD, the Bayesian inverse problem elliptic PDs, I guess the efficient sampling size for that important sampling is actually, well, for the high dimensions, it's actually like around the scale of 10. So I guess, well, it serves as a very good like guidance for the mode search. So I guess that in some sense works. But as for the HMC, I'm not pretty sure what does the effective sampling size means here. So if you could elaborate more, it would be better.
Okay, so here's the next one. How can you guarantee that the generative neural network map is invertible? Do you need to compute the determinant of the Jacobian of the inverse map?
Oh.
If so, what is the complexity?
I see. So for the invertible block, the design is actually the design is pretty much like we design a map that is some block that is whose Jacobians upper triangular, and we also design some block who serves as like the perturbation matrix, something like that, and we just composite them together. So the computational cost. So I mean, by design, it is naturally invertible, and the computation of the log determinant of the Jacobian is pretty much similar as a forward propagation. So basically, you should assume there's no extra cost for the Jacobian computation.
Okay, so here's the same question from the same person. Why did the ASVGD fail to capture the multi-modes? How did you choose the kernel width for ASVGD?
I see. So first of all, for the choice of kernel width, we actually search for a bunch of possible candidates and choose the best result we observe. However, as for why ASVGD failed, I guess the reason is that first of all, as we discussed before, the KO divergence, single-sided KO divergence, can have some local minimum, and also for ASVGD, the perturbation space, the candidates for that perturbation is spanned by the RKHS of the kernels. And if that space is not large enough, it is very hard for say samples concentrating at one mode to transport to another mode. And also there are some other issues with AES-BGD. So basically, there's no good guidance for the step size, and just as you said, for the kernel width. So essentially, in high dimensional space, they are, in some cases, they're likely to face mode collapse. Thank you.
So let me return this back to Alexei. Maybe you want to comment or you want to read?
I wanted to ask Tom about the number. How do you choose number of layers optimally? Do you, as far as I understand, you had 4 of them when you do the imaging of the faces, I guess.
I think it was 6, right? Suma, how many do we have?
Or at least you showed 4. But if you add one more layer, would it make things worse or better? How do you choose? When do you decide to stop?
I think for the elliptic equation, that the final layer is kind of it is a fine width size, right? 64 by 64. We start from A by A and so on.
Right. Yeah, but
for the image, I think there was no limitation like that, right? For the image, because that's no analogy of a mass size. I think more layer, the more accurate, right?
Yeah.
So but then maybe if you add more layers, you will start beating those state-of-the-art algorithms by far.
Yeah, Suma, will you comment on that?
So first of all, for the Bayesian inverse problem, we target at 64 by 64. Of course, we can, if we would like to do it on 180, 28, we can add one more layer. But adding too many layers will also, add to the burden of the memory cost, because training the neural network can be really expensive. So if in theory we can go layer by layer to infinity, but in practice, when the layer goes up, you have to pay for extra memory cost for memorizing the networks.
But Suma, we can also maybe do, instead of increasing by a factor of 2, we can maybe do a factor of half or some.
Yes. Yes,
right?
That is
then
possible.
It will be a better approximation, right? The Q tutor will be a better approximation of Q within smaller, more incremental increase, right, of the mass.
Mm-hmm.
So
then
you're
it's more layer.
saying that if you have infinite resources, you could have infinite accuracy? So the computational cost is the only obstacle in improving accuracy of your training?
You mean that could the training go to 0 in the error? Is that what you mean?
Yeah.
Suma, can you comment on that?
So first of all, at each layer, to do that, in each layer, you have to make sure that you capture exactly the QL at that layer, the posterior at that scale. So that means you will have a very large, infinite depth in depth network, and you train it for infinite time. That basically is infeasible. So I mean, at each layer we have some. We try to capture the posterior at that scale, but of course we have some error, and as the level goes up, those error could accumulate, and then in that sense you will have some limit, and beyond that you may just fail to capture the distribution.
Maybe we can also do a recycle kind of thing, like multi-grid. You can go back and then back to the coarse grid and then go up. Would that help?
Yeah, that might also help, but I mean, to scale up to infinite resolution, that could still be very challenging.
That's not realistic. Yeah, but I think that's a theoretical question. Yeah.
Well, thank you so much. I think we should move on with the next speaker. Thank you, Tom, again for your wonderful talk.
Thank you.
Thank you.